chapter 4. So chapter 4, previous lecture, we start talking about the definition of entropy, how entropy came from, how the defining entropy shaped the universal statement of the second law of thermodynamics. Today we have 2 points. We need to see how entropy is related to the work loss, and we need to explain the entropy balance, and then we can have examples. Even next lecture on Friday we will have more examples on this chapter. So the first part is relating entropy to the work loss. So far what we said we have entropy. Entropy starts with the definition of a state property can be calculated with Q divided by temperature for reversible processes. Then we said we can relate entropy to know the process is spontaneous or no by calculating the total entropy change. So we'll calculate the entropy change for the system, entropy change for the surrounding, sum both of them to calculate the total entropy change. And if the total entropy change is more than 0, so this means this process is spontaneous. It will occur without any external force. If the total entropy change is 0, so this means this process is a reversible process. And we said from the beginning, there is nothing in pure life, in real life, called reversible process. This is only an idealization, approximation of the process to facilitate the analysis to know the maximum efficiency, the maximum performance we can obtain from this process. Total entropy change can be negative, yes, but this means this process is non-spontaneous. So this process violates the second law of thermodynamics. This process will not occur by its own. Okay. Now we have another definition that relates entropy to work loss. So the whole idea of this one, based on the total entropy change, if the total entropy change increase, this means the total or the work loss increase or the efficiency will decrease. Okay? Because if you remember the total entropy change when it's 0, so the process is reversible. This is the maximum efficiency. So as long as the total entropy change increase, this indicates the process is spontaneous, but this indicates as well the efficiency of the process decrease. So entropy is related to the work loss, is related to the efficiency. Increasing entropy change means we have an increase in the work loss, the loss of work in the process. This means we have a reduction in the efficiency of the process. So how this came from, or how entropy is related to the work loss. Again, you will see a lot of math equations. I will not ask you to memorize these equations, but it's important to know the foundation of these concepts. So when we start with the first law of thermodynamics, first law of thermodynamics states du for closed system, du is dq plus w. We know that Q and W, heat and work, these are dynamic forms of energy. Again, recall it chapter 1. We have static forms of energy, dynamic forms of energy. Static forms of energy stored inside the system, which is internal kinetic potential. Dynamic forms of energy, energy that can cross the boundary between system and surrounding, which is heat and work. So we have heat and work, dynamic forms of energy, and these are also path function properties, depend on the process. So if the process is reversible, or if the process is irreversible, we have the same initial state, you have the same final state, but one reversible, one irreversible, then you have different values for heat, different values of work. Q and work depend on the path of the process you have. So it depends on the process is reversible or irreversible. So if we start with irreversible process, then we can say du, first law of thermodynamics can put it as du, the change of the internal energy, equal to the change of the heat transfer between system and surrounding, and the change of the work, actual work obtained from this process. Now, since we discussed about heat engines, we said heat engines are work-producing devices. So the ultimate goal is we need to obtain work. This work is done by the system. And any work done by the system, if we recall the sign convention we mentioned, work done by the system, it has negative sign. So if we consider this sign convention, we can say this equation, or the first law of thermodynamics for irreversible process, can be du equal dq minus the actual work. So far it's clear? Okay. If we have reversible process, so we can rewrite the first law of thermodynamics. But before writing it, we just need to recall from the previous lecture we said for reversible process, entropy is defined as dq by dt. So dq for reversible process is TdS. So we can say that, or rewrite the first law of thermodynamics for reversible process, du, we have du, dq, we will replace it with TdS, so this is dq for reversible process, and this is the amount of work obtained from the process if this process operates in a reversible way. So far clear? And again, if you consider the sign convention, we can rewrite the equation as du is TdS minus d work reversible. So we have two forms of the first law of thermodynamics. One we can use for irreversible process. It represents the amount of heat removed from the system. It represents the actual amount of work you obtain from the process. And here we have the first law of thermodynamics for a reversible process. We replace the dq with TdS, entropy definition, because this definition is valid for reversible process. And the amount of work from here is theoretical amount of work, reversible amount of work. Okay? So we said that we have Q and W, these are path functions. So do anyone remember internal energy, is it state function or path function? Let's back step. What is the difference? And anyone remember the difference between state and path functions? Path functions depend on the process, right? State functions depend on the process? No, depend on the initial and final conditions. I don't care how you move from the initial point to the final point. Only Q and W, path functions, care about the path, care about the mechanism, how you move from the first to the final point. But state functions, like internal energy, this does not depend on the path of the process. Only what is the initial condition, what is the final condition, and then I can calculate the internal energy. So here we have two equations to calculate internal energy. One, if the process is irreversible. Another one, if the process is reversible. And since internal energy is a state function, so do you think these two equations should be the same? So internal energy that you calculate from the first one, internal energy that we calculate from the second one, should be the same or different? If we have the same initial and final conditions. Same. Because internal energy doesn't depend on the process is reversible or irreversible. Depend on what is the initial condition, what is the final condition. What is happening in between? This will not change the internal energy value. So these two equations, they must be equal. Again, because internal energy is a state function. So if you calculate internal energy from this equation, if the process is irreversible, if you calculate internal energy from this equation, so you will have the same result. So you can say du is equal to dq minus dw, which is irreversible process, equal TdS minus d work reversible for irreversible process. Du is the same for both of them. Okay, so far is clear? Clear? Okay. Then we can say, if you put ds on the left side of the equation, rewrite the equation. So this is what we will have. ds, the change of the entropy, is dq by dt plus 1 over t, the work reversible, minus d work actual. Okay, and d work reversible minus d work actual, this represents the amount of work loss. Because reversible work, this is the theoretical, the ideal amount of work you can obtain from the process. If the process is reversible, if you don't have any friction. The actual work, this is the amount of work obtained from the process. If the process is real process, irreversible process, you have frictions, you have losses. So the difference between these two values representing the amount of work loss. Okay. So if we recall, remember that we said previous lecture, the total entropy change. This is the summation of the entropy change for the system plus entropy change for the surrounding. So for the system here, it has, like, we have some heat added from the system, we have some work lost from the system is doing some work. The surrounding is like adding only heat to the system, there is no work done by the surrounding in this process. So if you combine all of these equations, we can say the ds total, this is related to the d work loss, the term that we calculated here. And since we know from the previous lecture that the change of the total entropy change for like any process we have is more than 0, so this means always you will have amount of heat lost. And this indicates that, or by this derivation, we can say the entropy is related to the work loss. So if you make the calculations, if you have two processes and you calculate the total entropy change, for one process, total entropy change, let's say, is 2, for example. Second process, you have total entropy change is 4. So what these numbers means? Total entropy change means that, or indicates to the amount of work lost from the process, or the efficiency of the process. So if you have total entropy change as 2, or total entropy change as 4, this means the first process is more efficient than the second one, because the total entropy change for the first one is less than the second one. So far is clear? Okay. So this is the last concept that we have for the total entropy change. So by total entropy change, you can know two things. So what we said in previous lecture and this one, that we can calculate the total entropy change. And this total entropy change is summation of the entropy change for the system plus the entropy change for the surrounding. The value of the total entropy change, this one has like 3 possibilities. It can be negative, it can be 0, it can be positive. If the total entropy change, this one is negative, this means this process is non-spontaneous. This process will not occur by itself. It can occur if you force it to occur, if you apply external force to push this process in the direction that you want. Total entropy change is 0 if you have reversible process. And again, reversible process, this is an ideal process. It will not exist in real life, but just we are using it because its analysis is very simple. It gives you an idea of the maximum work we can obtain from the system, the maximum efficiency of this process. Total entropy change is positive. This is for spontaneous irreversible process. Irreversible process, this one means we have work loss. Because we have frictions happening in the system, so we have work loss. So since we have work loss, so this means the efficiency cannot be 100%. We have some losses happening. And if the total entropy change increase, so this means the amount of work loss, this also will increase and the efficiency will decrease. So this is how the total entropy change can give you an idea about this process is spontaneous or non-spontaneous, also can guide you of the efficiency of the process. So far is clear? Any questions? Okay. So as a summary for this, so as we said, this is what we were saying, that total entropy change for reversible process is 0. Total entropy change for irreversible process is more than 0. The work loss for reversible process is 0. The work loss for irreversible process, this is more than 0. So if you have process, and this process will produce work, okay, and you have two options. You can operate this process in a reversible way or irreversible way. So the maximum work you can obtain if you have run this process in a reversible pathway. So again, if any process that produces work, the goal is to obtain work from this process, and you operate this process in a reversible pathway, then this process or this pathway will give you the maximum work you can obtain. If you have process that require work and you operate this process in a reversible pathway, then the minimum work that can be consumed will be obtained in this case. So reversible process means if the process is producing work, then it will give you the maximum work you will obtain compared to any other process. If this process needs work to operate, so reversible process is the most efficient. The most efficient, what this means, it will take the minimum amount of work to give you the function you need. Okay, so it will make you the ultimate or the maximum savings. Okay, so the reversible process can be related to the maximum work or the minimum work based on the objective of the process. Is it produce work? Then you will obtain the maximum work for reversible process. If the process requires work, consumes work, so the minimum amount of work will be consumed if your process is reversible. Clear? Any questions? Questions? Sure? Okay. The last thing we have in this chapter is the entropy balance. So we did conservation of mass, we did conservation of energy, and now we will start the entropy balance. So the entropy balance here, this one is a mathematical formula of the second law of thermodynamics. Second law of thermodynamics says the total entropy can be created. Entropy cannot be destroyed. For any spontaneous process, entropy cannot be decreasing. It's always increase. So the total entropy balance can be expressed as this general way, similar to what we have in mass balance or energy balance. Accumulation equals inlet minus outlet plus generation. There is no consumption here. Okay. And usually when we have mass balance equations, we have here minus consumption. Remember, chapter 3, we always represent this consumption term. But in the entropy for a spontaneous process is always increasing. So there is no consumption in the general form of the entropy balance. So only we have generation. We have increasing in the entropy happening. If we start to put mathematics for this one, so we can say the change of the entropy of the system is the amount of entropy inlet to the system minus amount of entropy out of the system plus amount of entropy generated. Or we can represent the equation as rates. So this dot, if you remember, this means rate. Rate means you have property divided by time. So the rate of a change of the entropy of the system equals inlet entropy rate minus outlet entropy rate plus rate of generating entropy. So we have two forms. The first one is time independent. The second one is rate form. Rate form, we have the properties divided by time. So this is measured by rate. So let's see the name of each term. Delta S, this is the entropy change of the system. Delta S dot, rate of entropy change of the system. S in minus S out, this is not entropy transfer by heat and mass. Not necessarily inlet and outlet, but also heat and mass are affecting this one. Or the other side in the rate form, it's rate of net entropy transfer by heat and mass. S, this is entropy generation or rate of entropy generation. So this is the definition of each term we have. If we have multiple inlets, multiple outlets at the same time plus heat plus work, then we can say the delta MS, the entropy change, is the entropy of the inlet, or if we have many inlets, summation of these inlets minus summation of the outlets minus summation of Q over T plus S generation. In the rate form, we can have the same equation as this one. This is the general form we have for entropy balance. So based on the problem you have, you will need to start with any of these two equations. Okay, based on you have time-dependent form, or if you have rate form, based on the given information. You have mass given, or you have mass flow rate. You have moles given, or you have molar flow rate. So based on the given information of the system and the problem itself, then you can select any of these forms to start your calculation as well. Okay. You have tables in the slides. So these tables tell you the general equation, and based on the assumptions, then we can reduce these general equations into more simplified forms, similar to what you can see here. So this is the general equation we have. If you have closed system, then this term, the mass flow rate for the inlet and outlet, will be 0, and this will be the equation for closed system. If you have adiabatic process, then this term will be 0. If you have reversible process, there is no change in the entropy, so the generation will be 0, and so on. So you have here this table in these two slides that represent different cases and how to deal with each case. What is the term that will be cancelled from the equation based on the case you have? Okay? and we will go over this in the example. But just in case, when you are solving the example, just based on the statement, then this can guide you what is the term that will be cancelled in the general equation.